Right. What the industry began to use was the HRG system. Now, they use the HRG system for specifically the petrochemical and pulp and paper plants, much like they use the ungrounded systems, in that during a phased or ground fault, they did not want service or circuit interruption. Now, the benefit of the HRG system is it allowed the system voltage to be stabilized such that they did not have those high transient overvoltages as they did with the ungrounded systems. That's one of the principal benefits of a solidly grounded system, was that it stabilizes the system voltage such that you don't have transient overvoltages during arcing ground faults. However, due to the magnitude of current that was flowing, it was actually causing fires inside petrochemical plants, to the point that they got exemption in the National Electrical Code such that they did not have to have ground fault that might interrupt what they call a critical operating process. They would get exemptions. Now, with the introduction of the solidly grounded system, they began specifically employing HRG systems, or high resistance ground systems. Such a system actually inserts a resisted value into the circuit, into the ground fault return path, to limit the fault current flow from 1 amp to 10 amps, with the average being 5 amps. However, during a phased or ground fault, those devices must be taken offline. The circuit has to be interrupted after a certain period of time. And the reason for that is that you are dumping quite a bit of energy into the ground plane such that you can burn into the insulation of another conductor. For example, if your system is 40 volt 277 and I limit the current flow to 1 amp, that means that during the phased or ground fault, there is 277 watts of power flowing into the ground plane. Imagine yourself, for example, holding your hand on a 60-watt light bulb. You would not be able to do it for very long. A 100-watt light bulb, even less. Imagine your hand on a 277-watt light bulb. You can imagine the type of heat that's emitted. Now multiply that times 5. 277 watts times 5, if we limit the current to 5 amps, which is the average setting. You can get an idea how much heat is actually being generated. And in short order, that amount of heat will actually break down the vinyl insulation of the other conductors. Say, for example, you had a phased or ground fault inside of a conduit or condulet or a terminal box. That amount of arcing fault, though it's limited, it's not massive as you would have as an ungrounded or a solidly grounded system. You are still emitting quite a bit of energy in terms of heat. And if left continued there, it would actually melt the insulation of the other conductor, and then you would have a phase-to-phase fault, and your protected devices would operate. You would also allow a significant amount of fault current to flow that you could have a fire, which would impede the reason why petrochemical plants and pulp and paper plants installed HRGs to start with. Now, HRG systems are not something that you can install and just leave there. They have to be regularly monitored on a continuous basis, and when a phased or ground fault condition exists, they must be taken offline very, very rapidly. I've inspected hundreds of HRG systems, well over 100, 120, that I can think of right off the top of my head. And in the past 30 years, I've only found 2 HRG systems that were properly installed and maintained. Only 2. And usually they're associated with high-end petrochemical facilities such as DuPont or Conoco. They're very diligent, or have historically been very diligent with these type of systems. Now, what we're seeing in the industry is that facilities like data centers are wanting to go and employ HRG systems under the guises or intent of limiting the phased or ground fault currents that could occur in their facility, hence limiting damage, fire, injury. The problem with that is they have to be regularly inspected, regularly maintained, and they require someone that's experienced with these type of systems to install them and be readily available during a phased or ground fault. for example, if a data center is only manned by 7 to 8 hours a day and the rest of it is on automatic, you have a phased or ground fault, Murphy's Law being what it is, it's usually going to occur at a time where someone is not there. Statistically, they occur Monday mornings and Friday afternoons and at nights, where people either just coming to work or leaving or on at night when people are not about. The problem of it is you've left it unabated, unattended to. One, you would have to have someone that knows something about the system to be able to go and find it and alleviate it. Data centers do not maintain that type of expertise on board, and they don't maintain it 24 hours a day, which is one of the reasons we don't recommend this type of system for data center application. Even though, yes, initially it limits phased or ground fault current, if left unattended, very quickly those systems are going to evolve into a phase-to-phase fault. Those are the principal type of power systems that are involved in radial systems. Now, what began to occur in the early 1980s was we began to see in the industry a need for additional powers or a demand for additional sources of powers. Now, hospitals have always had standby generation systems, but what we began to see in the Square D company, beginning about 1983, we began seeing a rather rapid increase in the number of multiple-ended systems. By mean multiple, two sources, where a facility would have a utility transformer and a optional standby generator on site, or have the means to bring in a generator. That became very, very common. Beginning as we went up into the mid-80s and power systems began to expand, we began seeing a dramatic increase. For example, in 1983, we saw about 30 to 40 multiple-ended systems in a main-time main, two utility sources with a tiebreaker in between. And beginning in the 1980s, we began to see a rapid increase. Instead of having anywhere from 50 to 70 a year, we now began seeing hundreds of these coming through a year. For example, last year alone, the Square D Schneider Electric Company manufactured over 2,400 multiple-ended power systems in a 12-month period. Of those 2,400, there was over 50% that had more than two power sources. So what you're seeing now, it's no longer two power sources. We've had as many as 6, 8, 12 power sources, combinations of generators and utility power supplies. That gets us into what we call multiple-ended power systems. But let's talk about some of the basic principles that go on. What's happening when you tie two power systems together? And before we do that, we'll talk about some definitions. Okay, then we can get into the definitions.
The definitions that we got marked.
Yeah.
Okay. We're at 8 minutes, 41 seconds. Take 2.
All right. Before we get into multiple-ended systems, we're going to talk about some terms and definitions. I want to highlight just a few of them. There are many we need to talk about during the course of this presentation, and those will be explained to you. But the ones I want to talk about primarily, or principally four, I want to talk about the grounding electrode. Now, most people think of a grounding electrode as just a ground rod. However, a grounding electrode is the device that is used to connect a power system to the planet Earth. Now, typically it's a ground rod. However, it's not always a ground rod. It can be a water pipe. It can be the rebar in your facility. It can be your building steel. Or it can be actually buried copper wire outside your building. It's not always a ground rod. But what's most important is that whether you're using a water pipe or a ground rod, a ground ring, those systems must all be tied together.